A 1,600 kilogram weather rocket accelerates upward at 10 meters per second squared. So pretty much the opposite of gravity. At 1g, I guess. It explodes 1.5 seconds after liftoff and breaks into two fragments. One which is twice as massive as the other. Photos reveal that the lighter fragment traveled straight up and reached a maximum height of 6. Let's start by drawing a picture. We have a rocket, which is going to look like just a generic ball. It reaches this height up here, and it's going at V0, and this is some distance here. I'm going to call H. Let's call that H. And at this point, then, it explodes, and we have two pieces. One, oh, sorry, that's backwards. The massive one, the 2m, is on top. So this is m, and this is 2m. I'm going to draw the arrow for the speed of it going down, but I'm not actually sure if it's going down or if it's still going up. So that will have to be part of the calculations. So we want to know the speed of the heavier fragment. Oh, actually, and then I'm going to draw this top fragment up here. Goes a distance of h max. So we got a couple steps here we're going to do. So first thing we're probably going to have to find is, so this is a basically a collision problem, conservation of momentum. So the conservation of momentum is when it explodes, the momentum is conserved. So the momentum before the explosion, after the explosion is the same. But we need to know the momentum before the explosion, which means we need to know V0. So to know V0, we know that we have a constant acceleration. Therefore, we can use our kinematics equations to find out its speed when it explodes. And we can also find h. So we're going to go for both of those. So I'm going to write out the kinematic equations. So the way I write them out is I start by saying a equals a, meaning the acceleration is constant. V equals at plus v naught. X equals 1/2 at squared plus v naught t plus x naught. That's supposed to be an x naught. And then another equation I like to write out, which really isn't another equation, it's just the second and third one combined. It's final velocity squared equals initial velocity squared plus 2a delta x, where delta x is just the final position minus the initial position. All right, so we're going to start with this equation. I'm going to copy and paste it over here. So we're going to try and find our V0 in the picture. So I don't want to label it as something else other than V0. I'm going to call that V final. I know it gets kind of confusing because we're basically doing two separate problems here, but I'm going to call it V final just so that we don't get too much confusion. I'll try to minimize confusion. So V final, which is what we're looking for here, equals question mark. V initial is going to be its initial speed of the rocket. I assume it starts from rest. Yeah, we're going to assume that on liftoff it's not moving. Probably a fairly reasonable assumption. It's funny, it sounds like a joke when I say that, but I'm actually not sure. And then time, I think they said 1.5 seconds. So let's see, is that true? Mostly true, sufficiently true. Okay, so now we can find V final equals, acceleration is 10, time is 1.5 plus 0. Doing this by head, we get 10 times 1.5, which is 15 meters per second. Okay, so this, we know that this is moving at 15 meters per second at that point. Yep, that works out great. So now we want to find h. So for that, we're going to use the third equation here. And I like to write up the kinematic, whenever I do a kinematics problem, I just like to write up all the equations right in the beginning. That way I have them available, I can look at them, and the strategy with the kinematic equations is usually you want to find an equation where you have only one unknown. And then you go for that. All right, game face focus. X final equals h from our picture, our height. That is question mark because we don't know what it is. Acceleration, that's given to us. That's at 10 meters per second squared. Time, t is 1.5, and specifically 1.5 seconds. We're assuming that the v initial is 0, and we're assuming that when it lifts off from the ground. So we're going to say h naught is 0. Therefore, h, which is x final, this is x final on this side. I usually don't write the f there, but I probably should. That's going to be 1/2 times 10 times 1.5 squared. I think 1.5 squared is going to be 2.25. Not sure. That's okay. I'll do a calculator. 0.5 times 10 times 1.5 squared. And that's also 11.25 meters. And that's because that's 0 and that is 0. Okay, so now we have probably enough data for most of this. So from this point, yes, now I'm going to write out an equation for this second, or I guess the third picture, this scenario. So I'm going to say momentum initial equals momentum final, conservation of momentum. The explosion from the rocket, it all happens internal to the rocket, and since it's not an external force, it's an internal force. It's not going to affect the total momentum of the system. It'd be like trying to push your pickup truck from inside your pickup bed. It just doesn't work well. Nope. Purple is a good. Ooh, red. So I'm going to say that momentum, and I'm going to call this L and H for light and heavy. So the momentum of the entire thing, the light and heavy, is going to equal the momentum light plus momentum heavy. And we know that 2 mass lights equals 1 mass heavy. Basically, the light one has half the mass, or the heavy one has twice the mass. So then I'm going to rewrite momentum. Momentum is mass times velocity, so it's mass, light, heavy, velocity. I'll call this velocity, light, heavy. I know this notation, especially with this color, is looking a little bit too exciting for me. Mass, light, velocity, light, plus mass, heavy, velocity, heavy. So we don't know velocity of the light one, and we don't know velocity of the heavy one. So we want to find VH. So they give us a piece of data about velocity of the light one. So velocity of the light one, so H max, the maximum height here, is, I think they said 600 meters. And so for this, we're going to find the conservation of energy. So we're going to find out how the velocity of the light one has enough energy to travel up to a total of 600 meters. So I'm going to say that H max minus H, which is how far the rocket initially got up, so it travels up this far, and then it travels up to 600. I'm going to call that difference delta H. I'll draw that on the picture right now. So this distance, it's a terrible curly bracket, is going to be delta H. And that's going to be 600 minus the height it got to when it exploded, which we just found is 11.25. So not drawn to scale. So delta H is going to be 600 minus 11.25. If I was a better person, I could do that in my head. I'm not going to. So 600 minus second answer, 588.75 equals 588.75 meters. Okay, so we got that part. And if we do conservation of energy, so basically the kinetic energy from the lighter fragment flying up is going to be converted to potential energy of height. So 1/2 m, I'm going to draw a little L here for light, VL squared equals mg, and I'm going to use delta H here. So how much higher it travels from its initial position. So put a little L there, though it doesn't really matter per se because that is going to cancel out. So then the velocity light equals 2g delta H square rooted, which is going to give us, go to our calculator, second square root of quantity 2 times 9.81 times second answer, close, probably. And that gives us 107.5. 107.5 meters per second. Okay, so that is good, or at least important, because now we know VL. So we now know pretty much all of these values except for VH. So we're going to go back to our conservation of momentum. I'm going to copy and paste it, bring it down here so that we can look at this again. I'm going to start plugging in values that we know. And so rearranging this, I'm going to solve for VH. So I'm going to say that VH is mass light. Mass light plus mass H is going to be mass light plus mass heavy. Velocity of the combined minus mass light, velocity light, all over mass heavy. So I'm going to do one more. I'm going to rewrite this one more time. So this is going to equal mass light plus, the mass heavy is just 2 mass lights, velocity, light heavy, which we found. I think it was like 11 or something. We'll look. Minus 1.5, I think. Mass light again, times velocity light, which we just found, all over mass heavy, which is the same as 2 mass lights. This is a very bright color. Very bright. Okay, so now we can cancel out a whole bunch of the masses. So the mass here cancels, that mass cancels, that mass cancels, and that mass cancels. I'm just going to write a 1 there so we know it's 1 plus 2. So we have 3 times the velocity of light heavy. That's the velocity of the rocket when it just exploded, times velocity light, all over 2. So the velocity light heavy is the velocity of the rocket just prior to explosion, which is, did we find it? 15. So we have 15. So 3 times 15 minus, and 107.5. 107.5. 107.5. And we're going to divide that whole thing by 2. So then this gives us calculator. 3. Oh, let's do quantity. Quantity 3 times 15 minus second answer close divided by 2, and that gives us negative 31.2. Negative 31.2 meters per second. And that seems reasonable because the negative just means that it's moving downward. After the explosion, the heavy mass is moving downward, so which is reasonable. So, what is the speed of the heavy fragment just after the explosion? So I'm going to say the answer for that is 31.2, and I'm going to leave off the negative because they ask for speed. Speed, there's some people can have negative. Some people believe that you can have negative speed. Some people believe that speed is just the magnitude of velocity. For this question, it feels like they want a positive number. So I would say 31.2 meters per second. And then the second one was, what was the direction of the heavy fragment after the explosion? And that would be downward. And that's basically, when we do that's basically asking for the sign of the velocity. So downward means that negative direction. After the explosion, it was going down. All right. So we need to backtrack and kind of talk about how we went through this arduous journey here, this trek, if you will. So we're basically given a rocket. It shoots up, it then explodes and bursts into 2 fragments. So the explosion is conservation of momentum. We find how fast the rocket is going when it exploded and how high it was when it exploded by using the kinematic equations. And then to find out how fast one of the fragments was going so we can employ that into conservation of momentum, we use conservation of energy. So we were told how high the fragment, the lighter fragment, which was on top, the lighter fragment traveled straight up, which was on top. We were able to use conservation of energy because basically the kinetic energy from the fragment at the explosion was then converted to potential energy of the fragment at a height. We assumed that we neglected air resistance. And so then we found a max height. From there, we were able to find the speed of the lighter fragment as it exploded. We took all that data, put it back into our conservation of momentum equation. So this is conservation of momentum right here. Did a whole bunch of math. The right things canceled out because we didn't actually know the mass of the rocket. And we found an answer. So that was how we did it. This one was a bit cumbersome. It was basically like 3 separate problems all put into one. But each individual part wasn't too bad. So I hope that helped. See you next time.